Okay, good morning students. In today's class, we'll be discussing about production of antibiotics. And as far as antibiotics are concerned, there are n number of antibiotics, but as of our syllabus is concerned, it is streptomycin and cephalosporins are important. So we will be discussing only about production of streptomycin and cephalosporin. So let's get into the production of streptomycin. So this streptomycin is, of course, a broad spectrum antibiotic. It's aminoglycosidic antibiotic which works actively against gram-negative bacteria, and it's commercially available as hypochlorite with the formula C21H39N7O12 and 3HCl. So as in the previous classes I told, for any production, the microorganism is very, very important. So once you select the best strain of a particular product, most of your problem is solved. And then you need to take care about the conditions that are required or best for its growth and multiplication and the product recovery. So these things are to be taken care. So here in this case, Streptomyces graeus is the organism of interest, and here the spores of that particular organism are maintained in stock soil cultures. Then inoculum of this is inoculated into agar medium and kept at 28 degrees Celsius. After that, once it sporulates and build up the microbial network in the flask or seed tanks, it should be transferred to. So the production of streptomycin requires Hockenhull nutrient medium. It's of course name of the medium. You can just say streptomycin medium also. So with the composition like glucose of 2.5%, soy meal 4%, sodium chloride 0.25%, and pH of 6 to 7.6 to 8. So as such, Albert Charles from Rutgers University was the first to isolate the streptomycin in 19th October. So they have specified the date also, to that extent they are sure. So 1943. So he was a PhD student working under the guidance of great microbiologist, that is Selman Abraham Waxman. He is basically a soil scientist, or rather a soil microbiologist, who along with his interns discovered many of other antibiotics along with streptomycin. So it can be actinomycin, neomycin, clavacin, and various others. So this streptomycin was first medicine discovered for the treatment of tuberculosis, which was very effective. So according to WHO, that's World Health Organization, it is the safest medicine for treatment of tuberculosis. So it's been included in the list of essential medicines that are needed for health system by WHO. So in the year 1952, Walkman, won Nobel Prize in Physiology and Medicine for discovering streptomycin. So as far as production of streptomycin is concerned, since it is an antibiotic which is used to treat bacterial infections, and including TB, endocarditis, brucellosis, plague, rat bite fever. I mean, it has a wider application. So production of it is also very, very important. And Streptomyces graeus is the organism used, which requires media sugar in the form of glucose, fructose, sucrose, lactose, galactose, xylose, mannitol, maltose, or starch. Any of these things can be used. And along with that, it also requires fats, oils, and fatty acids as lipid source. along with, of course, the glucose sources. And nitrogen sources include peptone, meat extract, soy extract. Along with that, ammonium salts, nitrates, or glycine can be used as nitrogen sources. And proline is recommended for slow growth rate with large production of streptomycin. So just mere production of or rather the growth of organism is not sufficient. There should be growth. Along with that, major production or yield is very, very important. So growth stimulators like magnesium, calcium, and potassium can also be used. So it has three different phases. In the first phase, it will be just mycelial growth. So there we will just have to concentrate on the growth of mycelium. So once enough mycelial growth happens, then it is the second phase, that is streptomycin production phase. So here we don't want any new mycelium to be, that's where we discussed, slow growth. Okay, so once enough mycelial growth is done, then the growth can be slower, but concentrating more on the streptomycin production. So next, the third phase, mycelium undergoes autolysis with rise in pH value, and after a period of continued streptomycin production, the pH again falls down. So this is the basic, three different steps that are involved in streptomycin production. And then comes the recovery, wherein it is as such the mycelium. So, filtration has to be done, adsorption, elution, concentration, and evaporation and crystallization. So again, let us not go into the details of all these various recovery processes. Probably upstreaming process and downstreaming process, which you already would have learned, will be of more help here in describing about each and every step. So as for the examination point of view, one of the antibiotic production is very, very important. So just be sure that you know the procedure clearly. At least the organism, if you all know, then the upstreaming process, downstreaming process in your own way, you can write, of course, with a neatly labeled diagrammatic representation. It would fetch you more marks. Then coming to the streptomycin, as such, I have told you, it has a very wider use in the clinical science. It's very effective against gram-negative bacteria, used in the treatment of diseases like, tuberculosis, and it's used in conjunction with anti-mycobacterial drugs to treat pulmonary infections caused by, of course, mycobacterium avium complex, and it works as an alternative of penicillin G that's used for treatment of rat bite fever caused by Streptobacillus moniliformis, for those patients who are allergic or sensitive to penicillin. So instead of penicillin, you all can use streptomycin in case if the person is allergic to penicillin. Otherwise, maybe for that particular disease, penicillin may be the best one. So the products like streptomycin B and dihydroxy streptomycin can be obtained from streptomycin. Then also it is used for treating other diseases like endocarditis caused by enterococcus, and can also be treated with streptomycin if they are sensitive to gentamicin. So wherever sensitivity is found, to replace that sensitivity, you all can use this as an alternative. And plague, brucellosis, tularemia infections, all of these can be treated with streptomycin. So then, as far as agriculture science is concerned, streptomycin is used as a pesticide that inhibits growth of fungi, bacteria, algae, etc. So cell culturing, it is used at the time of cell culture to prevent the growth of undesired microorganisms. Of course, to prevent the contamination, we can use in case of cell culturing as well. So in biochemistry, streptomycin sulfate is also used in the purification of biomolecules like protein, and sometimes nucleic acids also. So next coming to cephalosporins. So the cephalosporins are also very important antibiotics. They are largest and most diverse family of beta-lactam antibiotics. So structurally and pharmacologically, they're related to penicillins, and they have a beta-lactam ring structure, infused to a six-membered dihydrothioazine ring. So thus forming cephem nucleus. So these cephalosporin compounds were first isolated from cultures of Cephalosporium acrimonium found in sewage of sewage. Okay, so they are, as such, I told you, chemically closely related to penicillins. Both work by inhibiting the cell wall synthesis of bacteria. So there are several generations of cephalosporins that we can encounter. The first generation cephalosporins entered the market in around 1964. Second and third were subsequently developed. Now, they are quite more powerful than the original ones. Now, fourth and fifth generations are also reaching the market. They have greater gram-negative antimicrobial properties than the older ones, which are more powerful against gram-positive organisms. So production of cephalosporins, as such, I told you, they are a class of beta-lactam antibiotics, um, and the scientists, credited with this Guy Newton and Edward Abraham. These cephalosporins are antibiotics chemically related to penicillins, derived from Cephalosporin C. They are effective against Salmonella typhi. This is the general structure of cephalosporins, and these are chemically closely related to, as such, we've discussed all of these penicillins, both work by inhibiting the cell wall synthesis of bacteria. And so each newer generation of these cephalosporins has greater gram-negative antimicrobial properties than the preceding ones. So the production method here, the fermentation process is very, very important, and it is similar to that of penicillin production. So the complex media with the corn steep liquor, meat meal, sucrose, glucose, and ammonium acetate are used, and fermentations are carried out as fed batch processes with semi-continuous addition of nutrients. pH usually will be maintained at 6 to 7. A temperature of around 24 to 28 degrees centigrade is feasible, and high aeration is necessary in the main growth phase. Oxygen absorption decreases sharply during production phase. So this biosynthesis of cephalosporin, if we look at it, so it proceeds from alpha amino adipoyl to L-cysteine and D-valine to isopenicillin N. As in the case of benzyl penicillin. The flow chart of this description is given in the next slide. You can have a look at it later. So in the next stage, penicillin N is produced by by transformation of L-alpha amino adipoyl side chain into D form via the action of variable resinase. So after the ring expansion to D acetoxy cephalosporins by expandase reaction, hydroxylation via dehydrogenase to D-acetyl cephalosporin C occurs, and the acetylation of cephalosporin C by an acetylcholine A dependent transferase is the endpoint of biosynthetic pathway in fungi, which could be clearly seen in this diagrammatic representation, wherein Cephalosporium acrimonium is being used. So this is the flow chart of cephalosporin production. So when coming to the mechanism of action, it inhibits bacterial cell wall synthesis as such, which is similar to mechanism that of penicillin. So the bactericidal action is exhibited by lysis of cell wall deficient forms. So finally, the important aspect here also would be the functions and use applications. It's stronger against gram-positive bacteria, that is Staphylococcus, Streptococcus, and including penicillin-resistant strains, effective against, along with Strepto and Staph, pneumococcus also. It is also, stronger against gram-negative bacteria such as Listeria, Pasteurella, Maltopsida, of course, Pasteurella species you can say, and E. coli and Salmonella. Leptospira are sensitive to this cephalosporin, and it's also mainly used drug in resistant Staphylococcus aureus, MRSA. And some gram-negative bacteria caused by serious infections such as respiratory tract, urinary tract infections, along with Staphylococcus aureus and E. coli infection. So it's active against, or rather it could be used effectively against both gram-positive and gram-negative organisms. Several of the organisms can be inhibited by using cephalosporins. So they have therapeutic use mainly in case of pharyngitis, tonsillitis, bronchitis, of course pneumonia, UTI, taken care, skin and bone infections, along with meningitis. But it also has several of the adverse effects like causing diarrhea, nausea, and vomiting, and pain and inflammation at the site of injection. Also, sometimes allergic reactions if a person is allergic to that particular chemical, and sometimes bleeding may also occur. So, with this, we are almost done with several of the products in this particular class, that is antibiotics. So, you concentrate more on streptomycin and cephalosporin. One will be mostly confirmed because as such I told you, you don't literally have to worry about if at all in some cases flowcharts would be given, and some it might not have been given. So for you, you have to literally worry about the organism that is important for the production and its parameters. Then you can write about the flowchart part of the upstreaming and downstreaming process in your own way. Okay, so thank you, have a great day.